Greetings, Earth enthusiasts. If you ever wondered about the incredible perspectives our planet has to offer from high above, you're in the right place. I am Dr. Clive Coetzee, and I'm thrilled to be your guide on this captivating journey into the world of remote sensing. Welcome. And please remember to like, subscribe to, and share this video. Thank you.
Our journey into the use of Sentinel daytime images continues. We took a little bit of a detour with the last 5 videos, 85 to 88, to play around with different platforms and different daytime images, and we just played around a little bit. But now our journey is focused. We're going to continue with Sentinel images as we generated from Earth Engine. Remember, what I want to do is to identify features or objects on Earth. Specifically, I want to look at urban structures, urban development, urban change, and so forth and so forth. So that's what I'm interested in. Okay, so I'm going to work with Sentinel. Its spatial resolution is much better than Landsat. So that's why I'm choosing Sentinel. However, the big thing is I don't have a lot of time. It's relative short in duration. So I only have about 4 or 5 years of spatial difference. Anyway, so we're going to continue. Okay, so we go to our trusted Earth Engine. We missed it. We haven't played around with Earth Engine for a while, so we miss it. Remember, first thing I want to do is upload my region of interest. There it sits, my region of interest. Okay, there's my region of interest. It's my trusted municipal area here in the west coast of South Africa, where the water is very, very cold. Anyway, quite a sizable area, covers a couple of towns, mostly farm area, agricultural area with either wheat type of things or cattle, sheep, and obviously a lot of grapes and things like that. Anyway, small towns, a lot of small towns, not major towns. Anyway, so that's our region of interest. We upload it. Remember, I add the region of interest to my map, and I give it a name, region of interest, a color. That's up to you, and I center it. And then I create my clipping tool. Now those are standard stuff. You should be very familiar with this. Nothing new. Okay. So that's always the beginning. Make sure you save, etc., etc. Or what we've done previously in many of our previous tutorials. Nothing new. Okay. So now, remember when we worked in both of the Sentinel Hub Earth Observation platform and with the Earth Explorer platform, when we identify our data sources or our satellites, our sensors, remote sensors, we must indicate the level of clouds. And obviously we want as little clouds as possible. We don't want clouds. Now sometimes when you're looking for a specific region, for a specific area or time period, and there is an image but it does have some clouds, not a lot, but it does have some clouds, you can still use it. There's methods how to take the clouds away, etc., etc., how to mask for clouds. But in our cases, we would prefer objects without clouds. Okay, almost a class without clouds. Okay, so our first thing is to create our clouds free script. Okay, so here we're saying what I've highlighted there, standard. It's in the, if you go to the data set and you go to Sentinel, remember we're working with Sentinel-2 images, and we're working with the surface reflectance. And if you go to its basic script, you'll see this it's located there. So there's that basic script. You can just copy and paste it. You don't have to go write it yourself, just copy and paste it. But basically we're saying we don't want clouds. Okay, we don't want any clouds in our image. Okay. Then we're gonna go and generate our 2 images. Now in this case I'm looking at the latest period, or the closest period as possible to the present time, which is 2024. Remember, Sentinel is roughly every 16 days, every 20 days, thereabout. So it normally gives you about 2 to 3 months to capture at least one or two decent images, because remember there's clouds and all these things. So give yourself at least 2 or 3 months room, because then at least you can generate at least one proper image for your region of interest. Okay, so I want to go as the closest period as present. So I've decided to go the 20th of January to the 30th of March, given that we're still in March. We're not end of March, so in fact that is more to the 14th. So this is about 2 months, just under 2 months. So we'll get at least one, maybe two decent images in this image collection. There's our ID. Okay, where do I get my ID? If you go to my landing page for the Sentinel, you see there's the ID. Okay, so there's the ID. It's exactly the same as this ID there. So I'm saying to Earth Engine, go to that specific data set. I want images from that specific data set. And obviously there's a hell of a lot of images there, so it's an image collection. But clip it for my region of interest, then reduce it for this particular period. I only want the images for this particular period for my region of interest, and has to be cloud free. Must not be any clouds. Don't want clouds. Okay. And call it Sentinel 2024. Okay. So we don't know how many images are there in 2024. This particular variable could be one, could be two. I doubt that it will be more than three, given the 16-day period and given the cloud 3 days and given the short duration here. But let's give it the benefit of the doubt. Let's say two. There's two images now lying here. There's two images lying there. Okay. And I want to go as far back as possible. Okay, understanding that, first of all, Sentinel starts from 27, end of March, maybe April. So I can't go 2017 there, because it doesn't exist. So I'm going to go 2018, and in my case I found that for 2018, for the first 3 months of the year, there's also no images. So I go to the 2019 period, and voila, I found some images. So that gives you 5 years of temporal difference. Okay, temporal difference, temporal meaning two periods, two images, different periods. I subtracted two different temporal difference. What's important in this case is I keep my periods exactly the same, meaning the first 3 months in 2024 equals the first 3 months in 2018, or 2019, sorry. That's very important. Okay, why did I call it 2018? I must actually call it 2019. Okay, so sorry, let's leave it now, but yeah, should be 2019. So where I said 2018, remember it's 2019. Why? Because of seasonal fluctuations. If I'm going to compare a January 2024 image with a July 2019 or July 2018 or July 2017 image, it's going to look vastly different, because July is in the height of the rain, everything will be green, whereas January everything is dead dry, it's just bare soils, basically dead vegetation, because it's in the height of summer. So that makes absolutely no sense to compare different periods with one another. And I did a video tutorial on this. So go and have a look at this video tutorial. Oh, come on. It's winter, summer. Where is it now? There we go. Winter versus summer. Tutorial 32. This one here. And you'll see the differences. Okay, you'll see there's some significant differences. Now, if you the whole year green, fine, no problem. But in our case, it's quite extreme, winter to summer, very extreme, so use the same period. So that's point number one. Be very certain you use exactly the same periods. Otherwise, your inference, your conclusions, your analysis would be, to be very honest, rubbish. Okay, so now we have after a present day image, and we have a past image. Okay, we have a present image and a past image. They are exactly the same in terms of the region of interest, the clouds, the period, etc. They're exactly the same, except the one is 5 years later than the other, or one is 5 years prior to the other one. Okay, so that's important. The next obviously important step is to understand that we have to apply our scaling factor. Now again, if we go into our landing page, you'll see each of these bands, bands 1, etc., are scaled. Now exactly why they are scaling it, I don't know. Why don't they just give it as a normal value, as a standard value? I don't know. Why they scale it, I don't know. But you can leave it at that, no issues with that, or you can scale it to its original values. Okay. Remember, it's normally from 0 to 255 or 0 to 260. I can't remember now exactly the number. Okay, so I don't like working in decimal, so I scale it. And this is the method of scaling it. So I take my images, or my images in that image collection of 2024, Sentinel 2024, and I multiply it by 1,000. So I take all those images, and I take each pixel of those images, and I multiply it by 1,000. That's why we work with the images, the full map, the image, and we multiply it by 1,000. And that returns then the scaled images, or scaled image. Now do that for both cases, 2024 and 2028. Okay, you'll see later why I've done it, and it should become clearer later why I prefer to work with whole numbers rather than decimal numbers. But I'll show you now later. Okay, make a note there. Remember that I say that. And then obviously, as I said, because I've got 2 months roughly, 60 days roughly that I cover, as I said, there could be 2 to 3 images. I doubt it will be more, but let's say 2 to 3 images, and obviously I want to reduce it to one singular image for that period. And I use the median. Again, welcome to go back into some of the previous video tutorials where I went through the reducers, and I keep on saying why, or we basically show in there why the median is the better option. Remember, you can use the first, meaning it will display the first one or the last one, or the mean, or the sum, or the maximum, or the minimum, whatever the case might be. Median seems to be the best fit or best reducer to reduce multiple images to a single image. Exactly the same as normal statistics. No different except it's an image, but remember the image are numbers. So we reduce those numbers to a median. Okay, and there we go. Voila. Okay, and then my visualization parameters 0 to 300 and true color. Now again, if we go to the landing page, you'll see the visualization parameters is decimals. Okay, now that's because it's unscaled, and here it's scaled. Basically, I multiply by 1,000. 0.3 times 1,000 gives me 300. 0 times 1,000 is still 0. And then I display the images. I add them to my maps. And if I want to, I can export them. So let's have a look and see how these images look like. Okay, let's have a look and see how these images look like. Here's my region of interest. Let's make it large and big. See if we can get it in. And I'm going to select my 2 images. Okay, so remember we created a median. Now I'm going to refer to 2018, but just make a mental note, it's 2019. Okay, not 2018, it's 2019. Okay, so there's my 2 images. Right, still loading. Still loading. There's 2018. There's, well, not there yet. There's 2024. Okay, 2018. Come on. 2018, sorry. There's 2018, 2024. 2018, 2024. 2018, 2024. 2018. Should be 2019, pardon me. 2024. If you look from this angle, you don't see significant structural change. Now, what I mean by a structural change, okay, so let me classify that, or my definition of it. Let's say there's a specific location. It has an object on the surface. Let's say it's a dam, water. That was in 2018. Now in 2019, there is a road. That means there's a structural change in that specific location. The object has structurally changed. It went from water to a road. That is a significant structural change. However, if it goes, for example, there's a dam, it's full, 100% full, versus a dam that's 10% full. Its spectral reflectance will be different. But there's no structural change. It's still a dam. The dam's spectral signature did change because of the difference in water levels. So that obviously will have a different spectral, but the structure is exactly the same. The structure of a dam with 90% water versus a dam with 10% water, the structure is exactly the same in terms of the spectral signature. However, if there's a dam and now there's a road, that means there's a significant change in the spectral reflectance, or spectral signature. That is a change in the structure. Okay, so that is what we're looking at. Look at locations where there's no structural change. Look to locations where there has been a structural change. But bear in mind, all locations will have a change. The difference is whether those changes are due to normal seasonal fluctuations or whether that change is because there's a significant structural change. Has the object of investigation changed, or is the object still exactly the same? The object has just changed a little bit because of the sun reflectance, or whatever the case might be. I hope that makes sense. Okay, so from here, from white, this angle, remember we're now very, very far above this region of interest. We look down and we say that was how it looked in 2018. That's why it looked at 2024. On first glance, there doesn't seem to be major change, but it's difficult because we're so wide, we're so far away. But we can't, with a naked eye, say, ooh, yeah, there's things that have changed. We need to go and have a look there. We need to have a look here. We need to have a look there. What we can do, obviously, is we can zoom into a specific location and then go and have a look. But it's going to take you a long time to go through this whole region of interest. So the bigger the region of interest is, the more time it will take to micro manage this, or to go on a micro level. So for example, we're going to go here and say, okay, let's isolate this particular area in my region of interest and let's investigate this area for whether there's any changes or whether there's been any temporal changes, spatial temporal changes. Okay, so let's have a look here. Okay, let's go. Remember, we can zoom in, but you can't zoom in too much because of the spatial resolution. So there's an optimum point where you have to stop in terms of, if you go further, it's blurring the image. Okay, so let's have a look at here and say, okay, let's compare these two images with one another. Okay, so we quite zoomed into a specific location. Let's just quickly make sure that these areas are loaded. Come on, let's make sure they do take a bit of time, okay? Okay, there's 2018. Have a look at this location here. Have a look at those. Looks empty. Doesn't look like much. There's some road structure there. There's some stuff there, but it doesn't look. Let's look at 2024. You can see, voila, built up. So there's definitely a structural change. There was vegetation, bare soil, open soil, vegetation, whatever. Now there is buildings. So that is a change in the structure of that object or that location. But let's have a look at this side. Look here. That's 2024 and that's 2018. No change. Yes, the color looks a little bit different and things like this, but it's fundamentally vegetation. There's nothing to it. We zoom in. Oh, come on. You see, that's the problem. Every time you zoom in and out, the whole thing, you have to reload, and it's really time consuming. But anyway, what can you do? It's one of those things. Especially if your internet is so slow. Okay. Come on. Why are you struggling? There we go. Okay, so sorry about that. Apologies. It does out of my control, unfortunately. But you can see there is this type of objects, or land cover or land use, typical. This is bush, scrubland type thing. And that was 2018 and 2024, exactly the same. Nothing different. Okay. So that is not a structural change. That is exactly the same. The difference in the spectral signature was because of seasonal change, seasonal fluctuations. A little bit wetter, sun a little bit different, it was misty that morning, whatever the case might be. Little bit different, but the underlying object is exactly the same, i.e. the structure of the spectral signature is exactly the same. But here we can definitely see, if you look at this particular location, If you look at this particular location, it's going to happen any moment now. This particular location, you can see there's been a change in the structural shape. That is 2024. This is now 2018/2019. Oh, come on. It happens when you zoom into, it does take a bit of time, sadly. So I hope you're starting to get the picture what I mean when I say, has there been a structural change or has been a seasonal change? It's a significant difference. And what we want to do is to identify locations where we experience a structural change versus locations that experience a seasonal change. Because what we want to do is to find out where has things fundamentally changed. Not cosmetically or seasonally changed, where has things fundamentally changed. So for example, here things have fundamentally changed. It was sand, it was shrubs, it was vegetation in 2018, and now it's built up. That is a fundamental change. But to do this now bit by bit by bit by bit for my whole region of interest is going to be very, very time consuming. So, except if you have obviously a very small region of interest, then you can do it by all means. Then you can do it micro manage, micro level, then you can do it. But with my region of interest, which is fairly high, to go bit by bit by bit, we'll sit here till tomorrow, and I need to sleep as well. So that's not going to work. Not going to work. So how can we get around this? How can we get around this? One is, not the only method, but one method is to calculate a spectral difference or to generate a spectral difference image. To generate a spatial difference image, a temporal different image. Sorry, I'm getting my words wrong here because I'm teased off about the slow speed. A temporal difference image. So we're going to create a temporal difference image. Temporal is time, difference is obviously the difference image. How do I do this? I basically just subtract the two from one another. So I create a new variable or new image, which is subtract. I know it's very original. You're welcome to name it whatever you want to name it. I name it subtract. As I said, it's very original, I know. Okay, so yes, so I get, and then I basically take the 2024 and I subtract 2018, just like standard maths. And then I'm giving it a visualization parameter, and I display it and I export it. Okay, so remember, I'm just putting these two numbers there because remember it's between 0 and 300. So if I subtract 200 from 300, I get 100. If I take 0 from 300, but the chances that it will be 0 minus 300 is very, very little. So I'm taking a punt that it will be somewhere between minus 100 and 100. You can change those numbers, that's up to you. Okay, so and then I press run, and what do I get? I get to an image that looks like this. Well, eventually. This is the temporal different image for my region of interest. So I've got the Sentinel 2024 reduced, clipped, scaled, zero cloud image. From that image, I subtract a 2019 zero cloud, same period, clipped, scaled image. Two identical images except the two time periods. I subtract those two from one another and I get this. This is I call a temporal difference image. Now that looks quite interesting. But now what does it say? What does this mean? So here I want to make some generalizations in terms of its color, in terms of its visualization. So if it is that color, then that's a seasonal change. If it's that color, that means this. If it's that, it means that. Otherwise, what's the point? Okay, so let's quickly go into specific areas and try to make from a very specific place, we're going to make generalizations and then use those generalizations to interpret this. I hope that makes sense. Okay, so let's go in here and see. Let's have a look and see. We've been to this specific location here. This is the one I normally go because this is the town where I stay. I'm familiar with this. I know what's going on here. I know what's going on here. Okay, so let's have a look and see. Let's first look at locations that had no change. Very little change. And we've identified them already. This one here. You can see that's 2018, 2024, 2018, 2024, 2018, 2024. Very little change. Okay, so let's see what that looks like. It's spatial signature. Let's have a look. So we go inspector. Let's click on it. Okay, a bit bigger. There we go. You can see that's 2024. It's spatial signature. Spectral signature. Sorry, my apologies. In 2024 for each of those bands. And there's its spectral signature for 2020. 2018/2019. You can see very little difference, né? Very, very little difference. Band 1 is the lowest, then followed by 2, band 3. If you look at band 3, it's got a value of, let's say, 72, and here band 3 has got a value of 60. So 12 points the difference. But you can see the structural change. Let's do this. Ah, come on. You see the structural change are almost the structural nature of the spectral signature are very, very similar between the two. So that means that location had very little change in the object. The object that was there in 2018, or the surface that was there in 2018, is pretty much still the surface that's there in 2023. There's been very little change. Visually, we can see it, and the spectral signature of the two periods basically confirms it. Now, if I subtract these two, I get something like this. So this, if I get a location and have a spectral signature of the temporal difference image, then I know there's been almost no change. The little change that was there was because of some minor seasonal fluctuations. I hope that makes sense. And you can see that. Let's have a look. There's band 4, 93 in 2024. Band 4, 70. So that means 93 and 70 is 12. So it's roughly 11. So if I go band 4, 22, what? Band 4 is 70, sorry. Band 4 is 70. And 92, yeah, so that's 22. Sorry, band 4, 70 to 90, 92, that's 20, that's 22, and that's a 22. So you can see this 2 is simply the subtraction of these two, which is what we've calculated. So here there's no structural change. The surface, the objects are almost identical, the same. Very little time have stand still there. No difference. That difference are marginal. It's in the error margin of error, so we can assume it's exactly the same. Then we get, so that gives you, how does that look like when we do this? How does that look in terms of the spatial, the temporal difference image? Grays. You can see these grayish areas. So when it's that sort of grayish areas, that indicates to us there that object or surface has stayed exactly the same. Very little change has occurred there. So first conclusion, grayish areas, these nothing color areas basically implies very little change. There's virtually been no change. What's there in 2024 was there in 2018. What was there in 2018 is there in 2024. Then we do have these two extremes, a very dark color and a very white color. Very dark color and very white color. Let's quickly zoom in and see what that basically represents. What that represents. So let's look at the dark color. Eventually, there's a dark color. So let's have a look at that dark color there. Let's click on that. Okay, so remember that's the dark color there. Let's click on it. Let's see what happened there. Let's see what happened. You can see this. The structure is very similar. So fundamentally, it's still the same object. Fundamentally, still the same object. However, there's been significant fluctuation in that object. So it's still, this is now, for example, the previous one where it was water was 90% and water was 85%. That was the previous example. Basically the same. Here, it's a dam, but where the water was 90%, now the water is 10%. It's still the same object because the structure is still the same, but within that structure, there's been a significant change. Okay, so it's a piece of land. Let's say it was sand. It's still a piece of land, but now there's grass. Okay, but you can see here it's negative. It's negative. So dark color same object, but the spectral signature has decreased. The spectral signature has decreased. It's absorbing more. It's absorbing more. Okay. Have a look there. There's band 4, was 153. There's band 4 in 2018, 318. So all of its reflectance have decreased over time. But it's, you can see the structure is still the same. Let's have a look at this one. Okay, so let's have a look and see how that looks. You see, there it is. Let's have a look at it in 2018. You see it's very bright. And then in 2024, it's very dark. But it's still basically a land, empty land. Well, not, let's say, not empty land. It's gone from soily to vegetation. Been gone from bare soil to vegetation. So it's very close to one another. Bare soil vegetation is very close, and that's why the structure is changed, but you still have significant change within the structure. That's very dark. So remember, very dark. Very dark goes from, very dark means you went from a very light place to a very dark place. Okay, now let's have a look at this place here. It's the opposite. It's very light. Come on. And you see now it's very dark. So this is now the opposite of what happened to this particular location. That second location that we looked at, that went from bare soil to vegetation. In this third one here, we went from vegetation to bare soil. So I bet you this is opposite. So this is an increase in spectral reflectance, spectral signatures. You can see that, an increase. But you can see the structure is very similar. You can see the structure is very similar, but there's an increase in spectral signature. So when there's a decrease in spectral signature, we, for example, went from bare soil to vegetation. When that's a decrease in spectral signature. We went from bare soil, something that reflects a lot, to something like vegetation which doesn't reflect a lot. Therefore, we have negative change in spectral signature. If we go from vegetation to bare soil, we went from something that reflected very little spectral signature to something that has a lot of spectral signature, and therefore there would be an increase in spectral signature. And therefore, but the structures are still very similar because we're still in the soil, open land type thing, where it's just where there's bare soil. So as I said, that's now very dark is where we have negative spectral signature change, large negative spectral signature change. When we have large positive spectral signatures, we have it very bright. Let's have a look and see. When we go to our temporal difference image, there you can see very dark, so grayish area, no change. Very dark, decrease in spectral signature. Very bright, increase in spectral signature. But the structures in all three of them, the structures have been pretty much the same. Nothing much to it. So let's quickly go to an area that did see some structural change, or in my mind did see some structural change. Remember, we've identified these locations. So let's have a look and see. Remember, there is bare soils. Let's have a look at, that was 20. Okay, so just again, let's give it a couple of seconds for this thing to get its mojo together. Let's have a look and see. Interestingly, this temporal difference image nicely highlights urban structures and urban areas, which is quite interesting. It does give a good indication of urban structures, of urban landscape. So it would be nice to generate two different images of a beginning and an end period and compare them. Maybe that's something we can do in the future. Okay, so there we go. I'm just quickly waiting for this thing to... So you'll see there in 2018 there's nothing, and 2024 there's something. 2018 there's nothing, 2024 there's something. So let's quickly then generate let's quickly just take it out. Let's quickly generate a spectral signature there. Let's have a look now. And now you'll see it looks very different. Oopsie, sorry. No, it looks still very similar. Let's go to it different. Maybe I just had my inspector at the wrong place. Here's one that think maybe I must use this one. Let's quickly go there and see. Oh, now it's going to take again. So there's a space there. That's what I want to look. There's some space here. There I know there's significant space. Because remember that was a house. I could just stand next to it and still in the garden of the house press the inspector. Okay, so that was 2018. You can see there, 2024, nothing there. See there? Ah, come on. 2018, nothing. 2024, 2018, 2024. So let's click on that. Now I know I'm at the right place. Have a look there. Now that is what I mean as change in the structure. You can say the spectral signature is totally different. It's totally different. The spectral signature, the element or the surface or the object that was there in 2018, sorry, you can see this, sorry, that one there. Make it bigger. The object that was there in 2018 is not the object that was there in 2024. There is something seriously different that happened. There is a change in spectral signature. The object fundamentally has changed. So I hope that makes sense. You can see there, you can see it's all over the place. It's not a nice change. It's not a stationary change, for example. That is a structural change. And how does that look? Let's have a look and see if we overlay the temporal difference image. Let's have a look and see. So you see it's very, very white. Again, very, very dark. Let's have a look at that area there. Let's have a look at that area there. You can see again difference in spatial in structure. So very light, very dark areas. Change in spectral signature. Dark, white, big change, but not necessarily a change in spectral signature. Very dark, very bright, structural change. Significant change in spectral signature. Dark, white, not necessarily a structural change, but a significant change in spectral signature. Grays, neutral colors, very little change. That's roughly the three conclusions, inference that we can make from this. So now obviously we can zoom out, and now it becomes much easier to, at this level with the naked eye, identify locations that on one hand experience very little structural change, objects are still the same, versus areas that experience some spectral change, which could be because of seasonal changes, and locations that experience significant structural change, meaning the object or the item on the surface has significantly changed. And you can see, let's say if you look at this, you can now see the areas that experience significant structural change are in the minority. You can see that the areas that experience significant structural change is in the minority. There's obviously a place that we need to investigate. There's a place that we need to investigate. There's some places that we need. So here, there's some areas that we can investigate. But in general, you can see that the areas that have experienced very little spectral signature change, meaning no structural change, are in the majority, versus areas that did experience significant change. And we're going to try to quantify this as well. By the way, remember what I said, why I don't want to work in decimals? This is why I don't want to work in decimals. I don't want to work in -2 and -3 and minus 0.04 and minus plus 0.008 and things like this. I want to work with 300, 210, 15, -10, -20. That's what I want to work with. And that's why I went with the scaling. But that's up to you. Okay. So this is quite neat, eh? This is quite neat. This is actually quite neat. And then obviously we can now play around with the visualization parameters. But it doesn't really make much of a difference. So if we go stretch that, remember when we do our visualization, we just change the minimum, maximum numbers, the range there. We do that, and let's have a look and see. It just highlights. You can potentially say these white areas, but now it just muddles the waters. Let's go stretch 90%. See how that looks. That becomes more like the general one. And we go states 100%. Nothing much to you'll see there. So playing around with the visualization parameters don't really yield much benefit in this specific case. Okay, it doesn't yield much benefit. Let's quickly run it again. Let's just unselect these ones. Not interested in that. Let's go a bit bigger. But I hope you get the idea that what we want to do is to use these images to identify locations or specific places where there's been significant change in the object or item on the surface of the earth. And I said you can do it's very difficult if you just look at the raw images to say anything meaningful about that. So that's why we create this temporal different image. And that allows us then to make certain broad generalizations. For example, areas where there's grayish neutral colors. Those are areas that pretty much look exactly the same today than it used to in 2018, 2019. So over the 5 years, there's been very little change. Those are areas where nothing much has changed. Then you have areas where there's still pretty much the same structure, but within that has been quite a bit of change. Okay, and then there's locations where there's been totally something now different. So if I went there in 2018, I would see a dam there. If I go there today, I would see a road. So that's, you know, the one where there's a significant structural change. The other one is where there's been significant change, but the structure plus minus have stayed the same. There was a dam, it was 100% full. I go there, there's still a dam, but it's only 1% full. Versus the one where there's no change, there's a dam, it's 100% full. There's a dam today, it's 99% full. So that's sort of the three broad categories that we generalize. And this is now nicely what we can look at this picture or this image. Okay, that gives us a nice visualization of this region of interest and how it changed or stayed constant over this period of time. Great stuff. Yeah, thanks, boys and girls. It was lovely having you on board. We're back on our road on Sentinel. We're going to ride this journey a little bit now. Please, I really ask that you like and subscribe and to share this video. More than 70% that watch these videos are not subscribers. I need your help, please, boys and girls. I need your help. I ask for your, I ask nice that you support this channel. There's so many things that I still want to do, and I believe this is quite beneficial and add quite a bit of value to your activity. So please like and subscribe, share this video, communicate with me if you need anything. I'll help where I can, and stay tuned. I'll be back very soon. Watch out for the next one. It's around the corner. It's underway, and with that, adios, and I'll see you on the other side.